Yes, it's Uncle Jegs, and today's video is all about the rates of reaction required practical. I'll first touch the collision theory, then I'll look at the theory behind rates of reaction. Then I'll look at the ways that we can monitor the rate of reaction, and then finally I'll run through the required practical itself. As always, check the description for today's worksheet and also the answers to the previous video's worksheet. Alright, let's get that tank. Let's look at this simple reaction. We have a diatomic molecule of A and a diatomic molecule of B. Di just means two, like dioxide and carbon dioxide means carbon with two oxygens. Our two diatomic molecules make two lots of AB. If this was a symbol equation, it will be written as A subscript 2 plus B subscript 2, arrow big 2 at the front of AB. The left hand side of our arrow is the reactants, the things that react together, and the right hand side is the products, the thing that's produced from the reaction. One idea underpins the whole of chemistry, and that is collision theory. Particles must collide or hit each other for a reaction to take place. But that sentence is not enough. I mean, you have oxygen molecules now slamming your lips, but thankfully you're not setting alight. So the particles not only must collide, but they must hit with enough energy to start the reaction. The faster they move, the more kinetic energy they have. The minimum energy needed to activate a reaction is called the activation energy. Have you clocked what happens in the reaction? The bonds holding the reactants together break and new bonds are made to form our products. The activation energy is used to break those bonds in the reactants. Take a look at these two graphs. The one on the left shows the concentration of our reactant as our reaction progresses. The one on the right shows the concentration of our product. Obviously, at the start of the reaction, we have 100% of our reactants and 0% of our product. We run the reaction and there is a steep decrease in our reactants and a steep increase in our products at the start. Our reactants are quickly colliding and turning into our products. But then there comes a point when the decrease in the number of reactants is so great that they have a hard time finding each other to collide to form our product. So the graph begins to level off. Then we get to a point which our line plateaus. This is where all or one of our reactants has completely reacted. There are several things that can make our reaction go quicker. We can increase the temperature, increase the concentration, which is the same as increasing the pressure, and also we can increase the surface area and add a catalyst as well. Remember from the last video on temperature change that temperature is a measure of the average kinetic energy of our particles. Two important factors occur when we increase the temperature. One, the particles move faster, so the time it takes for the particles to collide is shorter, and also they are carrying more kinetic energy. Therefore, there are more collisions that have the activation energy. Summarizing this, an increase in temperature increases the kinetic energy of your particle, which increases the amount of successful collisions. Concentration's a little bit different, and you should be careful how you speak about this. All we are doing with concentration is increasing the number of particles of one of our reactants, okay? We have not changed anything else. That means that the temperature is the same and the particles do not have more kinetic energy. The only reason concentration increases the rate of reaction is that there are more particles of one of your reactants. Therefore, they are more likely to collide with each other and lead to successful collisions. Surface area is an interesting one. It may seem counterintuitive that we increase our surface area when we crush our solid reactants from chips into powder. But think about it from the microscopic perspective. The individual particles of the reactants are the same size in both the chip form and the powdered form. The only difference is that in the chip, the particles are joined up in larger clumps. This means that not all of the particles are exposed to the surface. Therefore, these hidden particles cannot react with the other reactant. But the powdered form has more exposed surfaces, so the particles can collide with more particles in the same amount of time. Putting this into a sentence, increasing the surface area increases exposed particles, which increases the likelihood of successful collisions. Finally, we have the catalyst. We looked at biological catalysts in detail in my enzymes required practical. Check that out if you haven't done so already. Catalysts reduce the activation energy of a reaction by providing an alternative pathway. This means that the greater number of particles will have enough energy to react. This has all been well and good, but you need some sort of way to track how quickly your reaction has progressed. There are several ways of doing this. You could monitor a mass change, a color change, or the production of a gas. Since rate is something divided by time, for each of these we have to measure the time taken for the particular event to happen. A change in mass would be possible if the products formed, at least one of the products is a gas. If you leave the reaction vessel open, the gas that is produced can escape. If you place your reaction vessel on a scale, you can track the mass loss over a regular time interval. The particles that form your gas were initially part of your reactants, so the mass loss is the particles loss at a particular point of time, which can give us the rate of reaction. In reactions that produce gas, you could also collect the gas and measure how quickly you collect a certain volume of gas over a regular time interval. The less precise way of doing this is using an inverted measuring cylinder and a trough. As the gas is produced, it will displace the water, and you can use the new water level to measure the amount of gas you've collected. The more precise method of doing this is to use a gas syringe. The increased pressure from the gas form pushes a plunger inside your graduated tube that allows you to measure the volume of gas you've collected. The color change reaction is one that you are likely to encounter, especially in your exams, and this uses sodium thiosulfate. When reacted with hydrochloric acid, it turns cloudy, so you could use the time it takes for the solution to go completely opaque as a measure of your rate of reaction. There are two different activities that you can do for this rate of reaction practical. The purpose of them will be to investigate how concentration affects the rate of reaction. The first activity will follow a color change. This is the reaction between sodium thiosulfate and hydrochloric acid. This reaction produces sodium chloride, water, sulfur dioxide, and sulfur. Our dependent variable is the time it takes for the solution to go cloudy. This is due to this solid sulfur being formed. The technical name for a solid coming out of a solution is a precipitate. To have a clear cutoff point for your color change, you will have a black X on a white tile. So when you can no longer see the X, you can stop the timer. Our independent variable is the concentration of our sodium thiosulfate. To change the concentration, you will dilute the stock solution of your sodium thiosulfate. First thing, measure out your first volume of your sodium thiosulfate solution into a conical flask. Place this on top of the white towel with the black X on it, and then your water into the same conical flask. Then, using a different measuring cylinder, you measure out your specific volume of hydrochloric acid. As soon as you add your acid, start the time. Swirl the flask gently and wait. When you no longer see the X, you stop the timer and record your results. You repeat with the other concentrations of sodium thiosulfate. You then repeat each concentration 2 more times, so you have 3 repeats. This allows you to calculate a mean. A bit of safety now. This reaction produces sulfur dioxide, which can lead to some breathing difficulties. Don't sniff this thing, please. And for this reason, you make sure that all the windows are open, okay? The next activity you could do involves you recording the amount of volume of gas produced at a regular time interval. This reaction is between magnesium and hydrochloric acid. Looking at the results table, I'm using 2 different concentrations of hydrochloric acid and measuring this volume of gas every 10 seconds for 100 seconds. First thing to do is to measure out your hydrochloric acid using your measuring cylinder and pour it into your conical flask. Place your bung and delivery tube on your flask. Half fill the bowl or trough with water. Fill another measuring cylinder with water and invert it inside your trough so that there's no air inside the measuring cylinder when you stand it upside down. Cut a specific length of magnesium ribbon and add it to your flask. As soon as you do that, start the timer and measure the volume every 10 seconds. Continue until there's no more gas coming off. Then you record your results and repeat with your other concentration of acid. You can then use your results to plot a graph with the volume of gas produced on your y-axis and the time taken on the x-axis. Check out my video on how to think like a scientist to see how we draw tangents and gradients. There it is, ladies and gentlemen. The rates of reaction required practical. Check out the worksheets below and come back next week for the answers. Like if you like, hit the notification if you ain't done so already, and yeah, in a bit.